let's complete our first topic with a look at simultaneous equations. Now remember, the idea with simultaneous equations, the most common way of solving them is what we call the elimination method, because what we're trying to do is to eliminate one of the variables. And then we go and solve it for the other variable. And then once we know what that variable is, we can substitute back in and go and work out what the eliminated one is. Basic idea behind the elimination method. So let's just look at a basic example. We get something like this. We just need to make the coefficient of either the x or the y, it doesn't matter which, the same. Wonder which one I picked, x or y. Okay, so I'm multiplying the first one by 2 and the second one by 3, so I'm making the y's the same. So I come up with two new equations, but now the coefficient of y is identical. So I can do a subtraction, and I'm actually going to subtract the top from the bottom because I prefer positive numbers here with my x's. I get 11x is negative 33, so x is negative 3. Now I can go back and substitute back in and work out y. Well, whether you actually do the working out or you just do it in your head, that's up to you, of course. And so there's my final answer. X equals negative 3 and y equals 9. I deliberately chose x and y as the pronumerals here because you'll remember in coordinate geometry we often use this idea to find point of intersection of two lines. Now, if it is that sort of question, terrific, write your answer as a set of coordinates. That's not what this question is. It just happens to be that the pronumerals are x and y. So the correct way of writing the answer is not as a set of coordinates, but x is this, y is that. Here's one where I can't really do an elimination because whilst the actual pronumeral is the same, the indices are different. So I can't eliminate by multiplying by y or x or something like that. So this one we need to use the substitution method. That's a matter of making y or x, it doesn't matter again which one, the subject in one of them. Now, it makes more sense to use the linear function because you get a nice, neat thing to substitute in. So we'll substitute that. So y is going to be 14 minus 2x. Sub it into the second one, and I'll end up with a quadratic equation to solve. So let's turn it into a quadratic. Oh my goodness, multiplies together to give 615. Adds together to give negative 56. Oh, yeah, that's right. Oh, yeah, that's what I got too. Okay, so there it is, factorised. Two possibilities for x, which of course will mean there will now be two possibilities for y. We go back and substitute in. And I'll just write down the final answer. So we group them together, the different pairs. So x is 5, y is 4, or x is 41 on 3, y is minus 40 on 3. So that's what we call the substitution method. Of course, there's no reason why we just have to have two pronumerals. Any time you've got the same number of equations as you do unknowns, you should, theoretically, be able to solve them to get the pronumerals. Unless one is just the same as the other, but it's a multiple of it. So as long as there are three different equations, it should be possible. From a mathematical point of view, this would be 3 lines, but it's in a 3-dimensional number plane. And so these 3 lines going in all different directions, again, would meet at one point, and that's what we would find here. So, all right, let's do it. Oh, yeah.
They wouldn't always. To make a triangle, you know?
That's true if they're all on the same plane. Yeah, so that's why I say theoretically it should be possible if you've got the same number. So what we need to do is bring it down to a simpler problem. So we're going to now create 2 pairs of 2 equations and eliminate the same variable from both. So the first one, I'm going to multiply equation 1 by 2, and I'll get 2x plus 4y minus 2z, which I'll match up with the second one. And that'll allow me to eliminate the x. So I've matched up equation 1 and equation 2. Now I just need to pick another pair and also eliminate x. So let's just eliminate the x's, and there we go. There's my new equation. 7y minus 6z is minus 38. So if I now multiply the first one by 4, so I'm going to match up the first and the third equation here. If I multiply it by 4 and eliminate the x's, I now come up with another equation which just has y and z. So now I solve those two simultaneously. Okay. I've multiplied the second of my new equations by 6, so the z's will now eliminate. And I end up with y is -2. So now that I know what one of them is, I should be able to track back and get all the values. So if y is -2, subbing in, I've got z is 4, and now I can go back to one of the first 3 equations to work out x, and I get x is 3, and so there's my answer. These 3 lines would meet at x equals 3, y equals -2, and z equals 4. And of course, the fun thing about mathematics is, whilst we live in a 3-dimensional world, that idea keeps going. I mean, if we had 4 equations and 4 variables, we're talking about in the 4th dimension, and we've got 4 lines coming through in the 4th dimension and meeting at a point. We could find that point. There you go, 1h. In fact, we could have an infinite number of dimensions.